All right, these are our graphing ratio notes. So we're going to start by reviewing the parts of a graph. So it says on the graph to the right, label the following. So more than just label, I'm going to do some highlighting to help us out. So first we want to highlight that x-axis. So your x-axis is the horizontal line. So that's that. Here we'll label x. So this is horizontal. And it tells us to move side to side. That means that the y-axis is vertical, and it tells us to move up and down. And then another very big key feature is the origin. And the origin is that point 0, 0. So in this example, your origin is right here in the middle. And I forgot to label y up here, so I'm going to add that really quick. Our next question asks, how do we plot a point on the graph? So to plot a point, you find where the x and y value intersect and place a dot. Now, an important thing to remember when you're plotting a point is every point has the same order of numbers. So what I mean by that is every single point has an x value and then a y value. So you have to go side to side and then you go up and down. And I kind of think about that like the alphabet. X comes before y in the alphabet, so you have to go side to side before you go up and down. So a practice point for us to plot would be something like -2, 3. So we're going to start here at the origin, and we're going to move side to side to -2. So that's over here to the left. And then we're going to move up to a +3. So we're going to place our point right there where that -2 x value intersects with that +3 y value. You don't want to draw lines, and you just kind of want to put dots. If you need to draw the lines to get you to the right spot, make sure you erase them because there should only be dots. So let's talk about graphing a ratio. So we have example 1. We have Stephanie is driving her car to college at a steady rate of 50 miles per hour. The double number line shows the ratio of time to distance. Use the values from the double number line to fill in the table. So it looks like they're going to give us a lot of information here, so we don't have to do as much math. So the first thing they give us is this 0, 0. Okay, if Stephanie hasn't traveled, does it make sense that she's driven 0 miles? Yes, it does. The next point they give us is 1 hour, she can go 50 miles. They even told that to us here in this word problem. It says 50 miles per hour. So that's the first missing number in our table. 1 hour, 50 miles. Okay, then the number line tells us there are 2 hours, and that takes us 100 miles. And then 3 hours takes us 150 miles. And 4 hours takes us 200 miles. So if we kept the pattern going, at 5 hours, Stephanie could go 250 miles. 6 hours, she could go 300. And then in 7 hours, she can make it 350 miles. So on this table, we have our time values, which are the x's, because that's what happened first. And then we have the distance, which is our y. How far you go depends on how many hours you're traveling. So we're going to use that information to plot some dots on the graph. Again, lucky for us, they already gave us some information. They already plotted the point 1, 50 and 2, 100. So then this one is 3 comma, oh, you cannot see that, 3 comma 150. And then this dot up here is 4 comma 200. So if you look up at our table, the next point that we created was 5 hours and 250 miles. So 5 hours and 250 miles meets right there. And then we had 6 hours and 300 miles. And then 7 hours and 350 miles. And we didn't put this one on our table, but we could keep the pattern going because we know at 8 hours, it would take Stephanie 400 miles. And then down at the very beginning, they're missing that point at the origin of 0, 0. Because again, if she hasn't gone a distance, then it hasn't passed. Time hasn't passed, or vice versa. If she hasn't been on the road for any amount of time, she hasn't gone anywhere. She's staying where she started. So question A asks, is this an additive or multiplicative relationship? Since it starts at the origin, it has to be multiplicative. That means the only way to turn the x values into y values is to multiply. So our reasoning here is it starts at the origin, because anything times 0 is still 0. Oh, we already answered question B. Yay. Question B says, how far could Stephanie drive in 8 hours? So you could look at the graph, or we could follow the pattern in the table, or we could set up an equivalent ratio. So our starting ratio was 50 miles in 1 hour. We want to know how far she could go in 8 hours. So how do you turn a 1 into an 8? You're getting bigger, so you're multiplying. And more specifically, you're multiplying by 8. Whatever I do to the bottom, I do to the top. 50 times 8 is 400 miles, which is what we plotted on the graph and the pattern we were following from the table. Okay, the next question has us kind of working backwards. So for this problem, it says, how long would it take Stephanie to travel 450 miles? So again, our starting ratio was 50 miles in 1 hour. We're going to travel, well, she's going to travel 450 miles. So then the question is, how do we turn a 50 into 450? We got bigger, so we have to multiply. It's being multiplied by 9. Whatever I do to the top, I do to the bottom. So 1 times 9. It would take Stephanie 9 hours to travel 450 miles. Okay, example 2. We have Megan, and Megan is working out. She burns 225 calories every 30 minutes. So that gives us our starting ratio in the table. So 30 minutes is 225 calories. So we got to do some math to find the missing numbers. So to turn a 30 into a 10, we're getting smaller, so we have to divide. And 30 divided by 3 equals 10. Whatever we do to the top, we do to the bottom. So 225 divided by 3 equals 75 calories in 10 minutes. When we talked about the ratio tables, we do always want to try to start with the ratio they gave us because there's not a math error there. So we were given the starting ratio of 225 calories in 30 minutes. So we can turn a 30 into a 60 pretty easily. We can do that by multiplying by 2. Whatever we do to the top, we do to the bottom. So 225 times 2 is 450 calories. Now, we have to get to 50. Multiplying 30 by something to 50 sounds a little trickier than I'm wanting to do right now. So I'm going to use the 10. Because I can use any ratio because every ratio in the table is equivalent. So to turn a 10 into a 50, we're going to multiply by 5. Whatever we do to the top, we're going to do to the bottom. And 75 times 5 equals 375 calories. So again, we like to use the ratio given because we know there's no math error. But if it's easier to use another ratio we found, that is sometimes good as well. So from here, we're going to take these values and plot them on our graph. The graph over here tells us that calories burned is going to be on the Y values and the time are the X values. So remember when we talked about plotting a point, it's like the alphabet. X comes first, Y comes second. So on our graph, we're going to go over to 30 minutes, and 30 minutes is going to take us all the way up to 225 calories. So that plot is pointed. Okay, then we have 10 minutes is 75 calories. So there's our second point. Then we have 60 minutes. It's going to take us all the way up to 450 calories. And then at 50 minutes, it's going to take us 375 calories. We could fill in the missing numbers if we wanted, but we don't really have to do that today. So then our questions below, it says use the equivalent ratios in the table to complete the graph. Did that. And that's asking, are we multiplying or dividing? So here the question is, if Megan works out for 0 minutes, then in her workout, she also burned 0 calories. So this is multiplicative. And now time for some equivalent ratios. It says, how many minutes would Megan have to work to burn 150 calories? So our starting ratio was 30 minutes burned 225 calories. And we want to get to 150 calories. I don't know about you, but I don't know an easy way to turn 225 into 150 with multiplying or dividing. So we need to look at the ratios in the table and find a different starting point. And I think a better starting point would be in 10 minutes, Megan can burn 75 calories. Because from here, I can turn 75 into 150 by multiplying by 2. And whatever I do to the bottom, I do to the top. So it would take her 20 minutes to burn 150 calories. Question 3 asks, how many calories could she burn in 25 minutes? So we're trying to get down to 25 minutes. Then we're trying to figure out calories. So if I look at my ratio table, same thing. I don't really know how to turn 30 into 25 by multiplying or dividing. My next ratio on the table is 10 minutes is 75 calories. I think there's a way to turn 10 into 25 pretty quickly, but let's see if there's an easier ratio to start with. So we have 60 minutes. Don't know how to quickly turn that into 25. But our last one, I do. So our last equivalent ratio on the table is 50 minutes burns 375 calories. And we want to turn a 50 down into 25. So to turn 50 into 25, we got smaller, so we're dividing. We're going to divide by 2. Whatever you do to the top, you do to the bottom. So we have 375 divided by 2, which gives us a nice decimal answer of 187.5 calories. Alrighty. Our last example has us working backwards. So for this problem, they gave us the completed graph. And from the graph, we have to complete the table. So it's talking about cups of oats and cups of almonds to make granola. So here we have the oats on the x-axis, because that's the horizontal one, and almonds on the y-axis, because that's the vertical. So this first point right here is perfectly in between 4 and 6. So perfectly in between 4 and 6 is 5. So that's 5 cups of oats. And again, so 5 oats to 3 almonds, because 3 is in between 2 and 4. All right, our next dot is at 10 oats. Okay, so that's this number in our table over here. And 10 oats requires 6 cups of almonds. The next point on our graph right here, the oats is in between 14 and 16, so that'd be 15 oats. And 9 almonds. Neither of those numbers are in our table, so let's see if the next point is. Right here we have 20 cups of oats. That's not in our table. And 12 cups of almonds. That is this second point right here. So if it's 12 almonds, then it's 20 cups of oats. From here, we're going to have to find our other numbers by using our equivalent ratios from the table. So we're going to turn a 20 into an 80. We got bigger, so we're multiplying. And 20 times 4 is 80. Whatever you do to the top, you're going to do to the bottom. And 12 times 4 is 48. Same process. I want to turn a 12 into a 24. So I got bigger, so that's multiplying. And 12 times 2 is 24. Whatever I do to the bottom, I do to the top. And 20 times 2 is 40. So again, we're filling in the missing values in the table by multiplying and dividing. Whatever you do to the bottom, you do to the top. And then again, all of your values in your table give you x and y coordinates, which allows you to plot points on the graph. So A says if you are not given the table, but you're in just the graph, can we still create all these equivalent ratios? And that's yes, because we could pull the values from the points, those x and y numbers, and then multiply or divide. So question B says how many cups of oats would be needed for 18 cups of almonds? So I'm just going to use our starting ratio, which was 5 oats and 3 almonds. And we are turning the almonds into 18 because that's the new number given in the problem. So how do you turn a 3 into an 18? Well, you're getting bigger, so we're going to multiply. And 3 times 6 equals 18. Whatever you do to the bottom, you do to the top. And 5 times 6 is 30 cups of oats. Last one, we're going to use our same starting ratio from the graph of 5 oats and 3 almonds. This time we're looking for almonds. If we have 60 cups of oats, so oats are on top. So the question is, how do you turn a 5 into a 12? Sorry, how do you turn a 5 into a 60? And that's multiplied by 12. Whatever you do to the top, you do to the bottom. So that would be 36 cups of almonds. So again, ratio graphs are just another way to show those equivalent ratios in a different type of model.